Okay, this is a revisit. So sorry, there's a few technical difficulties in the last one. So hopefully you skipped the last few minutes of it. I just wanted to go back and re-explain this. So we know we got our slope. I think that's pretty straightforward. And then it's depending on where we identify it at. So again, if we draw our slope like this and weight coming down, then we can draw 45 degrees there. We draw 45 degrees there because we have a right triangle. And so when I did my calculation, my sum of the forces in the y, then of course I was going n sine 45 minus w. That would have been if my angle, since it doesn't matter because it's 45, but if I was using the convention with 45 in here, then this should have been n cosine. I think you can see that because if this is 45, then the cosine would be the adjacent side. So that would have been n equals w cosine 45, which again gave us the same answer, but just to understand the geometry. So instead, I used this angle up here, all right, which can be seen from if you draw a slope. So if you're not sure, you can also look at it from this perspective here. If you draw it more extreme, there's 80 degrees, 10 degrees, 80 degrees, 10 degrees. So if I want n sine of 10 degrees, if I'm going from that angle, or n cosine 80 if I'm going from that. Okay, so sorry for any confusion there. Um, so what that leaves us then with when we substitute, we take n and plug it into this equation, which we know is n cosine 45 equals weight over g, or mass times acceleration n, which we know, of course, is v squared over rho. So substituting everything, we get this. And this would normally be tangent of 45, but it's 1, which is the same as if you took the ratio of that. So I guess it'd be cotangent. But once we plug in our numbers, we get a value of velocity equal to 9.83 feet per second. All right. If I was better at Adobe Premiere, I would just go back and edit it and add music and effects, but that takes a long time, and I'm not good at Adobe Premiere, so it's going to be a little choppy. All right, so the last problem I want to do has to do with an incline and a race car driving around a track. So that one should be fairly straightforward and interesting also. And again, once you're done with all these, you'll have mastered the beginning of chapter 12. So here's our problem. All right, so let's go ahead and hold it up. Okay, so a curve in a speed track has a radius of 1,000 feet. So we know rho is 1,000 feet. And it's rated for a speed of 120 miles an hour. Now, rated speed. What is rated speed? So rated speed is the speed at which you don't rely on friction to hold you into the corner. So as you can see with this is as you go through the corner, your inertia is going to want to throw you out of the corner, but you have a mg sine theta of this angle of the weight of the car wanting you to come back in. And when you calculate it out, you'll find that it's independent of mass. It just has to do with the angle. So they design the corner in such a way that even if there's no friction, if it's snowy, the um, the amount of um, incline will hold you in the corner. Now, of course, if you exceed the speed limit, if you go into a 25 at 75, then friction's your only friend in that case. So that's what that is. And then, of course, when you have a bank turn like this, of course, there's going to be a minimum friction required because if you have no friction, for example, and you go through the corner, then if you go through it too slow, what's going to happen? You're going to slide down. So the problem is asking us really that the race car starts to skid. So that it goes through the corner and it's traveling at 180 miles an hour. That's when it starts to skid. So what we want to determine is knowing that it's 180 miles an hour, what is the coefficient of friction at that point when it just starts to skid? Then we want to go back and determine what is the minimum speed at which the same car could negotiate that curve. So meaning that if it just starts to skid at 180, how slow could it go and not slide back into the down the slope? All right, so that's the nature of it. So just like the other ones we've done, it's pretty much the same idea. Set up a free body diagram, identify your acceleration towards the center, and go from there. So take a moment to draw the free body diagram and the mass acceleration diagram. So pause and then draw it. Okay, you've drawn it. So let's see what it looks like. So here we have this. So we have our normal force, we have our friction, we have mg, all right? And then we have our mv squared over rho. Now we've tilted our axes, so that means that we're going to have mass acceleration in both the y and the x. So let's go ahead and sum the forces in the x equal to mass times acceleration in the x. And we're also going to sum the forces in the y equal to mass times acceleration in the y, since we know there's going to be both given the way we've done our coordinates. So if we go with the x first, we get what? Friction plus the weight, sine theta, equals ma cosine theta. All right. And we can see that over here. So if that's our acceleration, then in the x it's going to be cosine theta. So y is going to be sine theta. All right. So then if we rearrange this, we get F equals mv squared over rho cosine theta minus mg sine theta. And we'll leave that at that. All right. So it's our first equation. Then we're going to do the same thing with, so that's my x. Do the same thing with the y. So let's go ahead and draw a line. So sum of the forces equals may. What do we get? N minus w cosine theta equals ma sine theta. So if we solve for n in this case, we get n equals mv squared. Again, substituting acceleration for v squared over r, mv squared over rho sine theta plus mg cosine theta. So see, they're very similar, except negative sign and the sine and cosine are switched. Now, rated speed, that's the speed at which do you need no friction, right? So rated speed is V equals 120 mph, which we can convert to 176 feet per second. Remember, there's 5,280 feet in a mile and 3,600 seconds in an hour. So it's basically the conversion is just 5280 over 3,600, whatever that ratio is. So then you multiply that by that to get this. Okay, and if you, so what is that? I'm just curious. If I knew it at one point, 5280 divided by, and it's 1.466. So this equals 1.4667. So if you remember that factor, then anytime you have miles per hour, you just multiply by that, and that's going to give you feet per second. Okay. So if we assume that friction is 0, because remember it's the rated speed, it's the speed where you don't worry about it, then we can find the angle, because that's what we want. We want to know what the angle is. So we know F equals 0. So if we go up to this equation here, then we know that in this case, we know everything but theta. So we solve for it, we get tangent theta equals v squared over rho g. And this is an easy, just move it to the other side, divide both sides by cosine, masses drop out. That's how we get that. So the algebra is fairly straightforward. So if we plug in what we know, 176 squared over 1,000 times 32.2, remember the radius is 1,000, we get theta equal to 43.9 degrees. So that's pretty substantial angle, 43.9. When you think of the steepest hills, you're going to see in San Francisco are usually 8 degrees, 9 degrees. So 43, if I've been on a slope of 60 degrees in Australia and it looks literally straight down. So 43 might seem like not much, but that's a huge bank. So now we want to figure out what is our coefficient of friction, right? So the second part B is the coefficient of static friction between tires and track under the prevailing conditions. So what do they mean by prevailing conditions? They mean at the 180 miles an hour, right? Because he knows that this 43.9 degrees is the angle at which he can travel 120 or she can travel at 120 miles per hour around the corner without sliding out. But the vehicle is obviously going much faster. It's going at 180 miles per hour. So friction is going to have to play some role in it. So we know, so for part B, we know that mu, of course, is just the ratio of F over N. And we have a relationship for N. We have a relationship for F. So if we go ahead and solve, we get mv squared over rho cosine theta minus mg sine theta all over mv squared over rho sine theta plus mg cosine theta. So we can see that mass is still in there, and we're never given the mass. And as with all friction, or almost all friction problems, mass never really is a problem or needs to be known. And if you're not again, if you're not given mass and you're concerned, then just put in a mass of 1 kilogram or 1,000 kilograms, because if it's going to drop out, then make it easier on yourself. So now we need to simplify this. So here's the simplification. Let's go up here. So what I did is I multiply both sides by rho, all right? And so what that did is it allowed rho to go to here and here, get rid of it. So you get that. But if you multiply both sides by rho, the rho's drop out. That's nice. And you end up with v squared cosine theta minus rho g sine theta divided by v squared sine theta plus rho g cosine theta. So masses are gone, and we just have then our numbers, 264 feet per second. So that's what our 264 is how fast 180 is. So 180 mph times 1.466 gives us 264. So that's where that came from, 264 feet per second. We know our angle, we know the rest, plug it in, we get 0.39. All right, so that's the friction required. Okay. So then the last part is then how do we get out of the corner? How do we get the minimum? And so it turns out that in order to solve that, you just have to reverse the friction. And what I mean by reverse it, you just add a negative sign, because now if you look back at your original free body diagram, then up here, you see that friction is pointing the opposite direction, isn't it? If we're talking about how slow does it go before it's going to want to slide back in, and that's even with friction, right? So what we're assuming is that if this car were sitting idle on here at that angle, it would slide on its own. So even with 0.3, 0.43, and remember that what's the friction coefficient? It's 0.39. So remember how we determine whether something will slide or not, just based on the angle? If we take the tangent of that angle. Well, if we take the tangent of 43.9, well, what's the tangent of 45? It's 1. So we know that the if we take the tangent of this, we're going to get a number that's close to 1, which is much bigger than the 0.39. So that's how we're able to assume that if this thing is sitting on an incline, there's no way that it's going to not slide down on its own. So it has to have the v squared over rho in order to stay up on the incline. Otherwise, it's going to slide down. All right. So what we end up doing is we take the same problem and we just reverse the sign. Okay. So as I said, we have to reverse. So what we're going to do is we're going to take the friction equals negative mu n. So all we're doing is we're taking our original free body and we're moving this to here. Okay. So that's going to change our equation somewhat. Now we know that negative mu, right, is the same as F over N. That's what's defined as. So we put a negative mu there. Only now we know what mu is, don't we? We know that it's 0.39. And again, if you take the tangent of that angle, that's the minimum static friction that vehicle would need in order to sit still or not slide down without any help. So anyway, so we'll go through this, and then we have that equals that, and then we solve, and we end up with, when we solve this, we end up with v squared. And the easiest way to do it is to multiply both sides by the denominator, line up stuff, and just factor out the v squared, right? So if we move that to the other side, then move the v squared over to the other side, then, well, I can show you, but this is basic algebra, so you should be able to do this, solving for v squared. Move this to the other side, move the v squared over here with that v squared, move that over to the other side, and then factor things out. So what you end up with, isolating v squared as rho times g times sine theta minus mu cosine theta all over cosine theta plus mu sine theta. All right. So if we go ahead and plug in our values, we know 1,000, 32.2, sine of the angle 43.9, minus 0.39, cosine 43.9, cosine 43.9 plus 0.39 sine of 43. So you could plug that in yourself. So we end up with about 13 v equals about 13 what is it, about 115, I'm sorry, it ends up with about 130,369. That's squared though. So v squared is 13,000. Look at my calculator. Feet, yeah, feet squared per second squared. So you end up with a velocity of about 115.62 or 115.6. But we want miles per hour, so we convert back. V is in, this is in feet per second. And so it's about 78.8 miles per hour. So imagine having banks like that on every exit you go. So you have to go at least almost 80 miles an hour into the corner, or else you slide off the road. So that'd be a good excuse for not getting a ticket, I guess. All right. So I hope that helps. I hope you guys have a good week, and we'll see you back in class on Monday. Next Monday, what is that day? The 29th, unless things change. But I'll keep you posted on Canvas. Thank you again. Bye-bye.